So let's start off with the formula here. So the formula tells us that the number of combinations of n objects chosen k at a time is given by n factorial over k factorial divided times n minus k factorial. This is just another notation you might see. Okay, so let's do an example so you understand what we mean by combinations. So say, for example, your boss wants to form a 3-person committee from 5 workers: Sue, Jose, Ari, Pat, and Kit. How many different committees are possible? So in this example, note that a committee of 3 people, the order doesn't matter. I just have to choose 3 people. So Sue, Jose, and Kit, that's the same as Sue, Kit, and Jose. It's just the only thing that matters is which subset of the 5 people did I choose, but order does not matter. This is the essence of the idea of a combination. So let's suppose I were to look at these 5 people and just list every single possible committee. So let's say I start with Sue. Sue could be with Jose and Ari, or Sue could be with Jose and instead we pick Pat instead of Ari, or we pick Sue and Jose but Kit, right? So now we have all the combinations with Sue and Jose. So now let's suppose I put Sue with Ari and Pat, or I could put Sue with Ari and Kit, or I could even put Sue with Pat and Kit. And so those are really all the combinations that have Sue in the committee, right? So let's suppose I get, so Sue is out of the picture, and let's just look at Jose. I can put Jose on the committee with Ari and Pat. Jose can be with Ari and Kit, or Jose could be with Pat and Kit. And so let's suppose I've listed every single possible committee with Jose now. So the only other committee left is Ari, Pat, and Kit. So that gives me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different committees. And notice that I don't care about order. So this is really, SJA is the same as SAJ. So there's 10 possible 3-person committees. So let's suppose we use the formula now and verify this result. So in this case, I would say how many combinations are there if I have 5 workers to choose from and I'm selecting 3 workers. So using the formula, we have 5 factorial over 3 factorial times 5 minus 3 factorial. So that is 5 factorial over 3 factorial over 2 factorial. So if I just simplify this a little bit, I have 5 times 4 times 3 factorial over 3 factorial. And then I have 2 factorial is just 2 times 1. So I can cancel the 3 factorials. I can cancel this 2 with the 4, and that leaves me with 5 times 2, which is 10. And that's the same result we got by brute force here. So there's 10 possible committees. Here's another example that captures the essence of combinations where order doesn't matter. We're only interested in subsets. So let's suppose sundaes cost $8.95. You can choose 3 toppings for your sundae for that price. And there's 10 possible toppings total. So how many different sundaes are possible? So in this example, we're really being asked how many combinations are there? If I have 10 toppings and I can choose 3, like how many different combinations of 3 toppings are there? So again, we're going to use the formula. We have 10 factorial over 3 factorial divided times 10 minus 3 factorial. So let's just clean that up. It's 10 factorial over 3 factorial times 7 factorial. Now I'm just going to simplify a little bit. So I have 10 times 9 times 8 times 7 factorial, because I see the 7 factorial here. And then 3 factorial is 3 times 2 times 1. And then we have times 7 factorial. So I can cancel the 7 factorials, and then I can cancel 3 here, and I can cancel a 2 here. So that leaves me with 10 times 3 times 4, which is 120. So there are 120 different possible sundaes or combinations of 3 toppings if we have 10 to choose from. So let's do an example where multiple formulas are required. So 5 cards are chosen from a standard deck of 52 cards. How many 5-card hands have 2 jacks and 3 kings? Okay, so just to remind you, this is what a deck of cards looks like. So here are the jacks right here in this column. So there's the jack of hearts, diamonds, hearts, spades, and clubs. And we also, the kings are over here. So we have 4 kings. We have the king of diamonds, hearts, spades, and clubs. So I would approach this problem using the counting principle. So we want to know how many different hands of 5 cards have 2 jacks and 3 kings. How many different ways can I get 2 jacks? Like how many different combinations of 2 jacks are there? So we know that there's 4 jacks in the deck of cards, and we want to pick 2 of those jacks. And that's going to give us the total number of possible combinations of 2 jacks. So for example, we could get the jack of diamonds and the jack of hearts. Another possible combination would be the jack of spades with the jack of diamonds, right? So we just want to count how many different possible combinations are there. And we can do the same thing for kings, and we can think about that as stage 2 in a counting principle problem. So in this case, we would be counting, okay, so we know there's 4 kings total, and we're going to be picking 3 of them, and we want to know how many combinations are there. So this will become 4 factorial over 2 factorial times 4 minus 2 factorial. And then for this guy, we have 4 factorial over 3 factorial times 4 minus 3 factorial. So simplifying that down here, it's 4 factorial over 2 factorial times 2 factorial times 4 factorial over 3 factorial times 1 factorial. So we have 4 times 3 times 2 factorial over 2 factorial times 2 times 1, and times 4 times 3 factorial over 3 factorial, and 1 factorial is just 1. So I'm going to cancel these guys, and I'm going to cancel these guys, and that's going to leave me with 4 times 3 times 4 over, there's just a 2 left in the denominator. So that the final answer is 24. So there are 24 different 5-card hands that have 2 jacks and 3 kings. Here's a similar example just to kind of get you more comfortable with these examples. 5 cards are chosen from a standard deck of 52 cards. How many 5-card hands have 2 hearts and 3 clubs? So remember, in a standard deck of cards, so the hearts are over here, it's the whole row, and there are 13 hearts. And then we have clubs, and there are 13 clubs. So we're pretty much asking, how many different ways can we get a 5-card hand with 2 hearts and 3 clubs? So one example would be the 3 of hearts and the 5 of hearts, and then the ace of clubs, the 3 of clubs, and the 9 of clubs. That would be one example. So using the same idea as before, with the counting principle, I'm going to think about this as like stage 1 is picking my hearts and stage 2 is picking my clubs. So the question is, how many possible ways are there, different ways that I can get 2 hearts? How many different combinations are there of 2 hearts? Remember, there were 13 cards in the hearts, and we are just picking 2 and we want combinations. Order doesn't matter. And then same thing for the 3 clubs. We know that we have 13 clubs, and how many different subgroups of those clubs are there containing 3 cards? So again, order doesn't matter. So this is 13 factorial over 2 factorial. And then we have 13 minus 2 multiplied by 13 minus 2 factorial. And because the counting principle, we're going to be multiplying that by this quantity. And then we just have to simplify this down. So we have 13 factorial over 2 factorial times 11 factorial times 13 factorial over 3 factorial times 10 factorial. And then you can break this down. This quantity we have, let's see, 13 times 12 times 11 factorial over 2 times 1 times 11 factorial. And then this guy we can break down as 13 times 12 times 11 times 10 factorial. And then we have 3 times 2 times 1 times 10 factorial. And the reason I did that is because I can cancel these guys. So now I don't have any factorials. And I can simplify and cancel and simplify here. And I basically am going to get 78 times 286. So my final answer is going to be 22,308. That is the number of 5-card hands with 2 hearts and 3 clubs. So the last thing I want to mention is you might be wondering, when should I use permutations and use this formula, and when should I use combinations? So the basic idea is use permutations when order matters. So when you're arranging things and there's a certain ordering or arrangement, so it's much more, so you're being more careful, right? When order doesn't matter and you only care about who's in the group, order doesn't matter, use combinations. So here are some classic examples when you use permutations. Permutation, order matters, rankings like first, second, third place, gold, silver, bronze medal, job roles like president, vice president, secretary. Anytime you're scheduling, like say you're scheduling musicians and who's going to go first, who's going to go second, who's going to go third. Passwords, because of course 4721 is completely different from 7214. Order matters. Music playlists, like what order is the music played. So for combinations, these are some classic situations where order doesn't matter, like a committee where none of the people have any special role, so you're just picking people for a committee. Cards, like poker hands, toppings for pizza or sundaes, lottery numbers, the order doesn't matter. So anytime you have groups and sets where you don't care about the order, so like 1, 2, 3 is the same as 3, 1, 2. So that's when you would use combinations.